Alrighty, we are on chapter 20 now, carboxylic acids and their derivatives. In this chapter, we're going to look at the structure of carboxylic acids and the many similar functional groups that undergo many similar reactions, which we will call the derivatives. And so we'll explore all of those. But first, let's look at carboxylic acids and some of their properties. As we know, carboxylic acids generally carry the structural formula of having some R group bound to a carbonyl carbon, which also has a hydroxy group on it. And of course, it's called a carboxylic acid because it is fairly acidic, right? The pKa's of these are generally around 5 or so. So they're fairly acidic. Not as acidic as something like hydrochloric acid or sulfuric acid, of course, but much more acidic than something like an alcohol, right? An alcohol, the same molecule without the carboxylic acid, would have a pKa of around 15 or so. So just the ability of that lone pair to resonate can dramatically increase the acidity of your carboxylic acid. And if you remember way back when we talked about ARIO, right? Or we did CARIO. In this case, we're not going to worry about C or A or R or O. When we're comparing carboxylic acids, we can see that there will be pretty strong inductive effects, assuming the resonance is all the same because they're all carboxylic acids. We see, for example, that if we have carboxylic acids with more carbon-based groups, remember carbon-based groups are electron donating, as the carboxylic acid loses its proton, it forms the carboxylate, which resonates back and forth, right? And so we have electron density there. By putting electron donating groups on our carboxylic acid, we are destabilizing it. So this compound would be less acidic than something like formic acid, which has only the hydrogen here. This would have this one would be more acidic, or have a lower pKa, whichever way you want to look at it, as this lone pair resonates into the carbonyl. So we're going to end up with more acidic things if we have fewer carbon-based units, because remember, carbons are electron donating. By contrast, if we put electron withdrawing substituents on, if we put a chlorine on there, chloroacetic acid, we'll see that that will be much stronger than regular acetic acid because of that inductive effect. We saw that chlorines and other halogens tend to be electron withdrawing, which is going to stabilize it because we have extra electron density once we make the carboxylate, and that electron density is going to be alleviated a little bit by the inductive effect. So we saw that induction was an important characteristic when deciding about acidity. And remember, induction is kind of additive. If we put more chlorines on there, so same acid with now 2 chlorines, pretend that one's a chlorine, that will be more acidic. The more chlorines you put on, the more acidic. If they're fluorines, it's even more acidic than chlorine, because fluorine is a much better electron withdrawing group. If we put a nitro on there as well, we would expect similar results. And as we know, induction does decay over distance. So having the chlorine way over there versus having the chlorine directly on the alpha carbon, as it's called, we'll see that the closer the chlorine is, the better. So we want our inductive groups to be closer. So if we're comparing the acidity of these things, since they're all on oxygen, so atom is taken care of. Nothing's cationic, by the way. So atom is taken care of. Resonance is taken care of. They all resonate, right, through their carbonyl. And so induction is the next step. And the more, electron withdrawing groups you can put on, you can actually get carboxylic acids to be as acidic as hydrochloric acid. For example, trifluoroacetic acid, TFA as it is sometimes called, this has a pKa of about 0, so the same as HCl. HCl might be -1 or negative so, but very, very close. We're getting very, very acidic at this point. So we tend to see that. Carboxylic acids also tend to be really pungent smelling. So for example, lactic acid, something we've all heard of perhaps, is responsible for that sour smell of milk. Or if you have something kind of like some of these plant odors that can be pretty striking. You know, we've all smelled vinegar as well. That's a carboxylic acid. Those very kind of pungent, stinging odors tend to be carboxylic acids. And finally, because of all the hydrogen bonding that carboxylic acids can do, if we take a look at a set of them, carboxylic acids actually often form dimers that hydrogen bond with each other, just upside down. So the OH from one carboxylic acid hydrogen bonds with the carbonyl oxygen of another, and vice versa. And they form these kind of nice dimers. We often see them as such. So as a result, they often have very high melting points and boiling points as a result, because of these extra hydrogen bonds that happen. So just a little introduction to some of the physical properties and some of the chemical properties of carboxylic acids. In our next video, we'll take a look at how to name them, as well as how to name all of the many, many derivatives of carboxylic acids.